Okay, so I made the test up. There are 7 problems. It took me 18 minutes, something like that. So the first 5 problems are basically asking you to use various tests on that sheet that you'll have available. It's the sheet from page 644, which lists all the tests and the convergence criteria. And pretty much, not every one of them, but most of them you're going to use. So what I would suggest is you look at the handout, and hopefully I gave those back to you already. I think I did. I'm looking at my page of stuff. For most of you, I handed you back the one we worked on in class as far as the different tests and the verbiage used for it. So I'm just going to give you a flavor here. I'm not going to work every particular kind of problem, but you know, for example, if I gave you a series that looked like this, you have a geometric series. So if I gave you something like this, geometric series, so it's some ratio raised to the n power. There's 2 cases. There's the convergence criteria. If you look on your sheet of paper, it says for geometric series that if the absolute value of r is less than 1, it converges. And if the absolute value of r is greater than or equal to 1, then it diverges. So it's a matter of looking at this ratio, which is typically as a fraction. It doesn't have to be shown as a rational fraction. It could be a decimal. So I could have something like this would be another way of doing a geometric series. So it just has to be the equivalent value has to be less than 1 to converge and greater than or equal to 1 to diverge. So this one would diverge because 4/3 is greater than or equal to 1. This would converge. And then there's the equation that actually tells you what it converges to. A over 1 minus r, where A, in this case, A is 3, in this case, A is 4. And it works whether r is positive or negative. So if I had the summation from n equals 0 to infinity of, say, 8 times negative 0.2 to the n power. Now this would converge because the absolute value of negative 0.2 is positive 0.2, which goes here. So it would converge, and the value it would converge to is 8, which is A, divided by 1 minus negative 0.2. So that would be S is equal to 8 divided by 1.2, whatever that is. So that's geometric series. Then you have p-series a lot. Remember p-series, so this is geometric series. And I'm just going to verbally say what you would do. You can write it down, but you know, I would say this one, I would say this geometric series diverges because the absolute value of 4/3 is greater than 1, and therefore according to the geometric series test, the series would diverge, something along those lines. Then you've got p-series, and you know, you have 1 over n to the p. Now I could, you know, that could be summation from n equals 1 to infinity of 1 over 3 n to the second power. So the key thing is looking for n raised to some power. And the convergence criteria there is if n is, the p is greater than 1, then it converges. So this converges. All this 3 does here is just, it would give a third of the value, that would be equal to 1/3 the summation from n equals 1 to infinity of 1 over n squared. So anyway, that's a p-series, and it converges. You can look at your sheet when p is greater than 1, p is less than or equal to 1, and p is positive because it's always 1 over n to the p, where p is positive. Now there are cases where we use that within another type of test. So let's say we have the summation from n equals 1 to infinity of 1 over n cubed plus 5. And I asked what the convergence of that was. Well, this one is not exactly p-series because I have this plus 5. So typically when you have something that's like a p-series but has something added onto it like that, you can use the direct comparison test, and I'll tell you which one to use, so you won't have to, a lot of times it's the question, do you use the direct comparison test or the limit comparison test? And the direct comparison test is a little easier to do, so you'd use that if you had a plus type thing. And what that does is you would let a sub n be the original term in the series like this, and then you would let b sub n be the p-series, which doesn't have the 5. And the reason we can use the direct comparison test is that a sub n is always less than b sub n because we're adding 5 to it. So this denominator is always going to be bigger than this denominator for any given value of n. And therefore, we use the direct comparison test. And for that to work out, this has to be true, and let's just look in the book. And the other one is this has to converge. So a lot of times this comparison one is a p-series. It could also be, you could do the same thing with the geometric series. I could have, something like the summation from n equals 0 to infinity of 5 times 2/3 to the 2/3 plus, how do I want to do this? Yeah, I'm not sure. Yeah, okay, I know what I'm talking about. So if you had something like, 2 to the n over 6 to the n plus 3. In this case, this a sub n would be this, and you could use b sub n is equal to the summation from n equals 0 to infinity of 2 to the n over 6 to the n, which is equal to the summation from n equals 0 to infinity of 2/6 to the n. So this one, you could use the direct comparison test here as well by getting rid of that 3, and it would change into a geometric series. So a lot of times this happens to be p-series, but it could be a geometric series. So the way you would answer this question, what's the convergence of a sub n, summation of a sub n, is you would say, since b sub n is a p-series and p is greater than 1, b sub n converges. Then, since a sub n is always less than b sub n, the series, the summation from n equals 1 to infinity of 1 over n cubed plus 5 also converges according to the direct comparison test. Now if this were, let's say instead of adding 5, if we subtracted 5, you couldn't use the direct comparison test, because if you subtract 5, then a sub n would always be bigger than b sub n. So the way you would handle that, so what we're saying is, let's say you have summation from n equals 1 to infinity of 7 over n cubed minus 3 instead of plus 3. In this case, a sub n would be 7 over n cubed minus 3, and you couldn't use the direct comparison test, but you could use the limit comparison test, and you'd still write this out ignoring the negative 3, and b sub n converges according to p series. And the requirement for the other requirement for the limit comparison test is that the limit as b goes to infinity of b sub n over a sub n over b sub n, which in our case is the limit as b goes to infinity of a sub n, which is 7 over n cubed minus 3 divided by b sub n, which is 7 over n cubed. And you see the 7's cancel out, and you end up with a limit as b goes to infinity of n cubed over n cubed minus 3, which is 1. When n gets very large, this becomes insignificant. You can also do the coefficient ratio. You get 1, which equals a number. And because that equals 1, if it ended up n to the 4th over n cubed, then the limit would be infinity, and then therefore it would diverge. But in this case, it equals a limit, which is 1. It's not equal to 0, and it's not equal to infinity. So because that's true, and this converges, then this converges. That's kind of the way it works with the limit comparison test. And then you have alternating series. So with the alternating series, you have -1 to some power, n plus 1. And then you have the other part. Say it's 1 over n squared. So you have two requirements for the alternating series test. One is the limit as n goes to infinity of a sub n equals 0. In this case, a sub n is the term that's not -1, so it's just 1 over n squared. And that does converge. Now let's actually use this one. If this was not an alternating series, we just had 1 over n, it would diverge because it was a p series. But because it's an alternating series, it would converge because it would match that one. When n goes to infinity, this part 1 over infinity goes to 0, and the other requirement is that a sub n plus 1 is always less than a sub n, which, as you can see, is working. So this by itself would diverge, but by an alternating series it converges. Okay. Now there is a one where you have to find the radius of convergence. And find the interval of convergence. So that is where you use the limit test. You take the limit as n goes to infinity of a sub n plus 1 over a sub n, and you need for that to be less than 1. That's the requirement for any ratio test. But in this case, you have n, but you also have x, and then the whole idea is figuring out the values of x where this is true. In a lot of cases, what we end up with after simplifying everything down is we end up with something like you know, x plus 3 divided by 5. It has to be less than 1. So that might come about, you know, your original, let's say the original series was something like summation from n equals 1 to infinity of negative 1 to the n times x plus 3 to the n divided by n plus 5 times 5 to the n. So that's my original series, and when I applied this, the negative terms are irrelevant because we take the absolute value. The n plus 1 things, n plus something terms, when you take the limit as n goes to infinity, it just becomes 1. We've done that quite a few times. So you end up with these two terms. And a sub n plus 1, you have n plus 1 here, so when you take 3 plus 1 to the n divided by n plus 1 divided by 3 plus 1 to the n, you get 3 plus 1. X plus 3, sorry, x plus 3. Likewise here, you'd have 5 to the n plus 1 in the denominator and 5 to the n in the numerator, and it simplifies down to that. So from this result, what is the interval and what is the radius? So the first thing we would do is we would replace this absolute value thing with this. So the absolute value of this whole thing is less than 1 is the same as doing that. And this denominator, that's where you get the radius of convergence. So if it was 1, if you just add x plus 3 without a denominator, the default would be 1. But in this case, I do have the denominator. That's the radius of convergence. Now if I multiply every term by 5, I'll get negative 5 is less than x plus 3 is less than 5. And then I would subtract 3 from each term, and I would get that. So that's my radius. Well, this is my interval, except I have to do the endpoints, but the interval part is this inequality, or this term involving two x greater than signs. Now there may be equal or not equal, and you have to do the endpoints. We've done quite a few of those, so I'm not going to do anymore. You can look back at your notes. So that's the interval of convergence. And you can tell if you take 2 minus a negative 8, which is 10, and you divide by 2, that's 5. So that number, because what we're doing here, if you draw it on a number line, let's say this is 0 here, and that's 2, and that's negative 8. And the center point of this thing is x plus 3, but the center point is actually x equals negative 3. So that's the center of this Taylor series kind of arrangement. And so this is plus 5 to one side of the limit, or the interval, and this is minus 5 in the other direction. So it's centered around x equals negative 3. The distance from the center to the endpoints of the interval are 5, which is the radius of convergence. And the interval of convergence is this actual, what are the numbers is it between. So again, I'm not going to redo it, but check end points. And usually what happens, as you've seen in class, if you've been paying attention, is that a lot of times you end up in negative 1 to the, say, the n power, and then when you plug in x equals something into here, say for example this one, x plus 3, what you would normally have is, you know, one of the n's is going to be negative, did I do that right? Yeah, okay. So if I put in, say, negative 8 plus 3 to the n, back in the original expression here, this one, and I put in one end, you end up with -1 to the n, -5 to the n, and so that's -1 to the n, and then you have -1 to the n times 5 to the n. So you take the -5 and you break it up into a -1 part and a positive part. And then looking at these two together, you can combine you can add the exponents, you get -1 to the 2n. Well, that's even. So since an even exponent always gives you positive, these two terms come down to -1 to the even power, which is going to be positive, and so you just positive 5 to the n. Whereas when x equals 2, you get 2 plus 3, which is 5. So this is 5 to the n, and then you have a -1 to the n. Well, so we could say at x equals -8, we have an alternating series. No, a non-alternating series. Could be a p-series, it could be anything, but it's not alternating, so we have to use whatever it is. And at x equals 2, we have an alternating series. So when x equals 2, we're going to use the alternating series test. When x equals -8, we're going to use whatever the result is. And then the final problem is doing a Taylor series. So we've done Maclaurin series, we've also done Taylor series. And what I'm going to do is ask you to derive the Taylor series and then just do the nth number of terms. So I'm going to use e to the x. Make sure you know how to do sine or cosine. So I'll do the Taylor series. I'll tell you kind of what you need to understand as far as the other stuff is concerned. But so let's say you wanted to do, here's the function that you're trying to approximate, e to the x. And we did x equals 0. I think we did x equals 1, but we'll do it again here. So this would be Maclaurin series because we're centered around x equals 0. But we're not doing that. We're going to do f of x of e to the x. Let's say x equals -1 instead. Okay, instead of around x equals 1. So what does that mean? Well, it means that you're going to evaluate the function and its derivatives at x equals -1 instead of at x equals +1. If we did it around x equals 1. So it's like c equals -1. So you take the derivatives. So you take the first derivative, which would be just e to the x, and you actually let's do different, slightly different, not quite so simple. Let's say I wanted to do e to the -x instead. So the derivative of e to the -x would be negative e to the -x, and then f double prime of x would be equal to, you take -1. Using the chain rule, you get another negative, so then you get positive e to the x, and then you take the third derivative, and you get negative e to the x, and then you take the fourth derivative, and you get e to the and this all I forgot the negative signs in here. So you start with e to the -x, you get negative e to the -x, then you get positive e to the -x, negative e to the -x. Okay, so and we're going to evaluate all these at, we want the values evaluated at -1. So f of -1 would be e to the negative of -1, which would be e to the first power. F double prime of -1 would be negative e to the -1. So you get negative e, the first power. F double prime, that should be f1 prime. F double prime of -1 is going to be e to the minus of -1. So that's going to be e. And the third derivative of evaluated negative 1 is negative e to the negative 1, which is negative e, and the fourth derivative is a negative 1 is e to the negative of negative 1, which is e. So what you do is you evaluate the function at the center point, and then the polynomial that approximate that is f of c plus f prime. So this is the Taylor series. So instead of f of 0, you do f of c. F prime of c times x minus c plus f double prime of c times x minus c squared over 2 factorial plus f triple prime of c times x minus c cubed over 3 factorial. Okay, so finally you go back here and you find your value of the function. So f of c, which is negative 1, is e to the first power. Then you add f prime of c. Well, f prime of c. So f prime, single prime, is negative e. So you get negative e times x minus 1. C is the x value, and f prime of c is the value of the first derivative. Okay, then you get plus, so the next term is f double prime of c, which is positive e times x minus 1 squared over 2 factorial. Then you'll have plus minus e, this term right here, the third derivative, times x minus 1 cubed over 3 factorial plus e, this one, fourth derivative, times x minus 1 to the fourth over 4 factorial. And you can see the pattern. It's going to be plus minus plus minus. So let's go ahead and do the final one where we take the negative sign, just move it out. So you get e minus e times x minus 1 plus e times x minus 1 squared over 2 factorial minus e times x minus 1 cubed over 3 factorial plus e times x minus 1 to the fourth over 4 factorial. So that was 5 terms. So when I talk about the number of terms, if terms go to 0, don't include those. So for example, like, the cosine of x around x equals 0 is equal to, let me see if I can find my sheet here. It must be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial. So that would be 5 terms. I don't count the ones that go to 0, which are the x cubed. So this is 5 terms. So, what kind of thing might I give you? Well, I might give you the function is the sine of x, and x is 2 pi. Or I might give you f of x equals the cosine of x, and x equals 3 pi over 2. It'll be one of these multiples of pi over 2. And so obviously it's not one of those, but just think about what you would do. You're going to end up with some kind of alternating thing, depending upon which angle it is. So cosine, if you had cosine of, instead of 0, which is what I used here, was around x equals 0, if you have the cosine of pi over 2, then it's probably going to be, this will go to 0, and this will be, the x term will be there, and the x cubed, and the x fifth, and so forth. Now I'm not going to ask you about proving the convergence. I just want you to derive a polynomial, a Taylor series polynomial of n terms, which I specify, and just clean it up at the end. And it's going to be either sine or cosine, and it's going to be some multiple. It's not going to be x equals 0 because that's the way we did in class. So it's going to be, negative pi over 2, positive pi over 2, pi through pi over 2, 2 pi, something like that. I could do it around, like pi over 4, and that would be even more interesting, but I'm going to have mercy on you. So that's it.